All right, guys, today we're going to look at reaction rates, specifically reaction rate law. And with that being said, let's go ahead and get started. This is the calculation, so you're going to need this equation down right here, and I'm going to point out the parts of it. So, rate, what this is a reaction rate. So molarity per second, if you remember that. So molarity per second, we find this experimentally, is equal to K. This is called the specific rate constant. Depending on the reaction, right, this will change. So for certain reactions, if it was A and B, they stay the same. And depending on the temperature, okay? So it's a constant as long as the reaction and the temperature stay the same. However, if you change the reaction or change the temperature, that number changes. All right, we have something in brackets here. So A just represents whatever chemical you want. It's a reactant. This is reactant A. It's in brackets, so it must be the molarity. It's to the M power. What we're going to put here is something called the reactant's order, right? And it's going to be that power. We'll explain that in just a second. And then once again, bracket B, so the concentration of reactant B to its power, to its order. And then if you had a third reactant, it would be bracket C, and so on and so on. All right, with all that being said, it's sometimes easier to do these problems or look at them. So first of all, I'm going to show you, well, how do we determine the order of a reaction? So what we need is some data here. Let's say that we had reactant A and reactant B, okay? I'll put them in brackets because we're going to look at their concentration. So let's say we start off with a 1 molar concentration of A and a 1 molar concentration of B. Okay, let's say when we did this, the reaction rate, okay, so its reaction rate was, we'll just say 2.0 molarity per second. All right, so this is our first reaction. Now, to be able to do this, you actually have to do more than one reaction. You have to be able to compare. So, how to best test this is to double one of the reactants at a time. So we're going to double the concentration of A. We're going to leave the concentration of B the same. And so, if this occurred, let's say that the rate went up to 4.0 molarity per second. All right, we've doubled the concentration of A. We kept B the same. So we're just going to look at A. So we've doubled this. So I doubled the concentration. All right. What power do you have to take that to? In this case, right here, we've doubled the rate. So I've doubled the rate. So 2 to the, and I'll put this as an M, I guess, since we have an M up here. So 2 to the M power equals 2. You double the concentration, I doubled the rate. Well, hopefully you know that M would be equal to 1. So this would be considered a first order reactant. Okay? This would be considered a first order. Again, what that means is if I double the concentration, the rate will double. That's what first order means. Okay? Let's continue on a little bit here and say, okay, well, let's look at this. Let's take A back to being just 1.00 molar, and let's double B this time. And let's say this happened, that when we did this, the rate was 8.0 molarity per second. Okay, I'm going to compare trial 1 to trial 3 now. It does not matter which order you compare in. You compare any trial to any trial. But I want A to stay the same because I just want to look what happens when B doubles. So compare A, or trial 1 and trial 3. A stays the same, B doubles. Okay? So we have B doubling to the N power equals, well, what happens to the rate? It now goes 4 times faster. It quadruples. So I'll put a 4 there. So 2 to the N power equals 4. N would be equal to 2. And we would call this a second order reactant. So when the concentration doubles, if the rate quadruples, we call this a second order reactant. Okay? If we doubled the concentration and the rate went 8 times faster, so let's say this said 16.0 molarity per second, it went 8 times faster, this would be N to the third power. Okay, hopefully you're seeing this. So, if I double the reaction or concentration and the reaction rate goes 8 times faster, this is a third order reaction. If it went 16 times faster, it would be a fourth order, and so on and so on. All right. So we're going to scroll over here. All right, we're going to examine this data. I want to do a number of things. I want to determine the rates for both of these. I also going to look at, we're going to show you how to find K, and I'm going to show you how to look at the overall order of the reaction. So let's get this thing to work. All right. So here's our data. We got A and B again, so just some random numbers here. And so, all right. So we have trial number 1. A is 1 molar, 0.1 molar, B is 0.1 molar, and the reaction rate is 2.00 times 10 to the negative third. All right. Trial number 2. We double A, keep B the same. If you look, what happens to the reaction rate? Uh-oh. Right there, if you can tell, it doubles. So, if the concentration doubles and the reactant rate doubles, if you remember, this is called a first order reaction. So we're going to scroll down here, and here's our equation. So now we're going to write rate is equal to K, bracket A, to the, it's a first order reactant, right? Because we doubled the concentration, the reaction rate doubled. So A to the first power, okay? Let's look at the other one. So now what we'll do is we'll compare 2 to 3. This one says 2.0, so these stay the same. This now doubles, so now we have the doubling of B. So I'm just now going to compare it going from 4.0 to going to 16.0. So what happens there? Well, that quadruples. It goes 4 times faster. So if one goes 4 times faster, we call that a second order reaction. So we're going to put B to the second. So now I've written out my equations with the order, right, for both of those. If a question asks what is the overall order of the reaction? Well, it's very simple, okay? So if you're going to do the overall order of the reaction, all you got to do is add up the order of A plus the order of B, and this is a third order reaction. Okay? So this is a third order reaction. I guess I should put third there instead of just order. This is a third order reaction overall. All right. How is this helpful? Well, I can predict if I start doubling concentrations and tripling and stuff like that, I can actually predict in time how quickly the reaction will occur, and it should, if our calculation's right, occur right when we want it to go off. All right, one last thing. How in the heck do you find K? Well, what we're going to do is we're going to plug in the information we know here. So I'm going to come back up here, pick a trial. Pick one trial. You're going to use all the data from one trial. It does not matter which one you pick. I'm going to pick these because they have ones with it, and I like ones. Easy to calculate. Okay, let's try that again. So, both of them have a 0.100 molar concentration, and our rate is 2.00 times 10 to the negative third. So, for the rate here, I'm going to plug in 2.00 times 10 to the negative third molarity per second is equal to, I don't know K, that's what we're going to find, times 0.100, remember that's the concentration of A, to the first power, times 0.100 molar to the second power. Okay, I go grab a calculator. Here we go. All right, so I'm gonna do this side first. So I'm gonna keep this as 2.00 times 10 to the negative third molarity per second is equal to K. I'm going to go ahead and multiply those out. So 0.1 to its own power is the same thing. 0.1 to the second power gives me 0.01. I'm going to multiply those together. All right. Now, the number here when I do this is 0.001. Okay? So 0.001. Now, that molarity is to the first power. This molarity is to the second, and I'm multiplying them. So this actually turns into molarity to the third power. All right, I want to solve for K, and right now what I'm doing is multiplying these times each other. So to get to the other side, of course, I want to divide. So let's do that. So I'm going to divide this by 0.001 molarity cubed, this by 0.001 molarity cubed. Those cancel out. Well, let's look what I'm going to be left with. So K is equal to, let's get the number first. Alright, this comes out to be a nice number. And I guess those actually, with sig figs, those should have a couple more zeros added on. Sorry about that. So with sig figs, this will give you 2.00. So there's my number, 2.00. And then, look what happens here. 1 molarity divided by molarity cubed. So that molarity cancels out with one of those. And they're being divided, so you're going to write this as 1 over molarity squared times seconds. Or we can write this as molarity to the negative 2 seconds to the negative 1. You've got to be careful here, and I know a bunch of you don't like to write out units, but depending on what your order of your reaction is, this unit here actually for K can change. It can be different. So it's not always going to be 1 over molarity squared seconds. It can change. Alright. Based on all that, we might as well do one more problem here. So this is asking the same thing that you'll see with your worksheets and stuff. Alright. What we want to do is write the formula, reaction order, and then solve for the rate constants, okay? So rate is equal to K times A to the M power B to the N. Let's look at some of these. All right. A reaction concentration doubles. All right, comparing 1 to 2. Look what happens to the rate here, though. Do you see what happens? It actually does nothing. All right. Well, in this situation, we double the concentration, but the reaction rate stays the same. So if I was to look at this mathematically, double the concentration, so 2 to the M power is equal to 1. Well, hopefully you know this. M is equal to 0. We call this a zero order reaction. All that means is, when you double the concentration of this, nothing happens to the reaction rate. Concentration actually does not factor in for A. Okay, so we call that a zero order reactant. So we're going to plug in rate is equal to K times A to the 0 power. Let's see what happens with B. So A stays the same. We double B. You can see the reaction rate. What happens to it? It doubles. If you remember, that's a first order reaction. So B to the first. All right, here is our equation. Fine. So that was answer 1. Remember, it asked for 3 parts, so answer 1's there. Overall order. Well, 1 plus 0 is 1. So this is a first order reaction. Lastly, it says to find K. So I'm just going to take some numbers to plug in. I'm going to start with our beginning here. Rate is equal to, plug in for rate. Our rate is 2.00 times 10 to the negative third. Molarity per second is equal to K, what we're trying to find, times 0.100 molar to the 0 power times 0.100 molar to the first power. I like this one. This doesn't take much calculation. Alright, so 2.00 times 10 to the negative third molarity per second is equal to K. This is going to be 1. Anything to the 0 power is 1. Times anything to the first power is itself. So, times 0.100 molar. Divide this over. Those are going to cancel out. K is going to be equal to 2.00 times 10 to the negative second. Molarities actually cancel out on this one, and for this one, all you're left with is 1 over seconds for your units. Alright? So, that's rate law for you. That's how you calculate these. Please ask any questions if you have them. Write them down. Bring them to me tomorrow. And we'll do some calculations with this tomorrow. All right.